Assalamualaikum warahmatullahi wabarakatuh. Um, Dear all students, I hope all of you are doing fine. So our lecture for this week is will be done using this virtual platform. So this week we're going to cover the topics on roots of equations, solving for multiple roots and non-linear equations. If we can recall, last week we have covered topics on open methods to find the roots of functions, and earlier on we covered topics on bracketing methods to find the root of equation. So this week is an extension for the topics that we have learned for the past 2 weeks, and this time around we deal with polynomials or functions which have more than one roots, um, or multiple roots. So this is an example of mathematical functions or polynomials which have more than one roots. Okay, the first one, we have third order polynomial equations in which we have at least two roots, and another one is a fourth order polynomial equations in which we have um, at least three roots. Okay, so there is a limitation for bracketing methods that we have learned in the past 2 weeks. So bracketing methods is only applicable or useful when the given function has a single roots. In the events where a function's polynomial equations, in other words, the polynomial equations of higher order, okay, third order, fourth order, and so on, they usually have more than one root. So the bracketing method is not useful or applicable in this case. So we have to use open methods such as Newton-Raphson methods, second methods, as well as fixed point methods. And this week we come on to this another methods known as modified Newton-Raphson methods. Okay, so this is an extension of Newton-Raphson method that we have discussed last week. So this modified function is useful in the events where both fx and f prime x, the differentiated form of fx, are 0 or approaching 0. Okay, so when this situation happens, the Newton-Raphson and second method that we have learned last week becomes ineffective. Okay, so this is the formula for the modified Newton-Raphson methods. Okay, so you can refer to your notes and see how it's being derived. Okay, so in order to use this Newton-Raphson method, so we need to do some additional steps. So we need to differentiate the original function by 2 times here, as given in these equations. Okay, so I will demonstrate to you shortly how to use this function. So again, when this modified Newton-Raphson method is useful, so it's preferable for multiple roots, even though it's not really efficient. Okay. So this method involves laborious, laborious computation effort. So it's only used when it is really necessary. Okay. So let us start with our first examples. Okay. So this question asks us to use standard and modified Newton-Raphson methods to evaluate the functions. This is an example of third order polynomials. So the initial guess of x naught is given as 0. Okay. So I have done some initial works on this. Okay. Okay. So this is um, the function. This is the function. Okay. Uh, x to the power of 3 minus fx squared plus 7x minus 3. So remember the question asks us to find the roots using the usual Newton-Raphson method, this one. Okay. This one in yellow. And also use modified Newton-Raphson methods. Okay, so I start with the usual Newton-Raphson method. So these are the terms that we have to work on. Okay, we start with x, starting with the guess value of 0, and then we need to evaluate fx, f prime x, and finally the resulting x. So okay, so let us start with the first iteration. So we start with the value of 0. Okay, right, 0 here. Okay, and then evaluate the function. Okay, so this is our function, x to the power of 3 minus 5x squared plus 7x minus 3. So I have already write down the formula here in my Excel cell. Okay, this is x to the power of 3 minus fx squared and so on. And then the prime fx, so we have to differentiate the original function. So the we have to so the differentiated form of the original function is 3x squared minus 10x plus 7, right? Okay, and then we plug in the initial value of x equals 0 here in our f prime x function. Okay, and then finally use this formula, okay, to evaluate the new value of x. Okay, so this is the first iteration, so there is no relative error to be calculated. So we proceed to the second step. So we make use of the previous value of we use the value of x which is previously calculated here in our as our new guess value here, right? Okay, and then we repeat the same step as the first iteration. So apply new guess value of x into our original function, and then repeat the process just like we did in the first iteration for the f prime x, and then use the formula to get the new value of x. And here we can, starting from this point onwards, we can evaluate the approximate error. So by finding the difference between the new value of x and the old value over the new value times hundreds. Okay, so you see here, so for the second iteration, it is 37% of approximate error relative to the first iteration. So we repeat for the third iteration using the value of x previously calculated. Okay, and repeat the same step all over. So we can continue on with the fourth iteration. Okay. Right, so we have to keep repeating this until we reach 0.0% of approximate error. But it's not mentioned here, but it's good to keep doing the iteration until we reach 0.0% error. Okay, so it's always very convenient to do this in Excel. Of course, during the real test or exams, you need to demonstrate um, the actual equation, your calculation manually. Okay, you see that our error is decreasing as we doing more iteration. We have to keep doing this until we get the 0.05 target. Okay, right. So a bit more. I don't know. Maybe we have to do this more than a dozen times to get to the value that we are looking for. Okay, here seems that our value is converging. Okay, I think one more iteration will suffice. Okay, so we have to do up to 12 iterations to get to the value of error that less than 0.05. Here we see that um, the value of x is almost 1. Okay, and you see that as we continue on using doing the iteration, the value is converging, so that tells us that we are doing the right thing. Okay, so let us start using this modified Newton-Raphson formula. Okay, so if you notice, so this is the equation that we have to use. So we have the formula is slightly different, in which we have additional we have to differentiate the original function by 2 times. Okay, and the rest are just the normal iteration that we normally carry out for any numerical method analysis. Okay, we start with the first iteration, the initial guess value of 0. So we plug in this initial value of x into the value of function here. Okay, and so same thing for f prime x and then f double prime x. So here, if you see, I have differentiated the original function by second times for the second times. So the f double prime x double prime x is 6x minus 10. Okay, so everything is normal. You just plug in the value of x into the function, and then we get this. Finally, we get this new x value using this equation. Okay. And I repeat, for the second iteration, use the x value that we have previously calculated. Okay, and then repeat the same process, right? So let us do more iteration until we get to the target. Okay, so you see that we converge to the final value of x pretty quicker than using normal Newton-Raphson method. Here we just use 4 iteration to get us to the target value of approximate error, which is less than 0.05%, and this is the root that that we are looking for. Okay, So it gave almost similar value, okay, to the normal Newton-Raphson, but at much quicker converging rate. Okay, so that's for the first part of this lecture. So wait for the next series of lecture that I'm going to deliver shortly.